Okay, good afternoon. We'll be talking about humanoid walking based on inverse kinematics. We will go in a little detail about this topic, which is inverse kinematic, which is very useful for a lot of things, of basic things in research, but it's necessary to learn about it. The agenda that we'll be covering today is as follows. First, we will talk about workspace versus joint space, then direct kinematics, inverse kinematics, the manipulator example, which is a pedagogical example. Then we will extrapolate this to a humanoid. Then we will propose some humanoid walking motions. Then we will mention some words on dynamics. We will briefly mention the case of now, some differences with other systems that we will be reviewing today. And finally, we'll try to make a little demo walking. As you can know, walking is almost covered. Some roads, like now, has a built-in walking feature, but we are interested in propose our own walking engine and to know how can we manage this basic tool for humanoid. First of all, many of you know this, but many undergraduates still don't know this kind of stuff. So there are two different spaces in robots that are joint space or configuration space. This is the angles of each articulation. For example, for this industrial robot, we have 6 degrees of freedoms, 6 articulations, and they are all actuated. And on the other hand, we have workspace, task space, or even operational space, which is composed by the position and orientation of the frame attached to the final tool. This is X, Y, Z, and phi, theta, psi, which are Euler angles and Cartesian position. So the trick here is to transform a point in the joint space into a point in the task space. This is called direct kinematics, and the inverse procedure is the inverse kinematics. This is a standard procedure which is easy to do with the right tools, and this is more difficult, and there are several ways to do it. We are going to solve it by geometrical equations. This is based on Spong book, on the book of Professor Spong. So for the manipulator example, we will be reviewing what is the inverse kinematics. So first of all, it is easy to explain with a computational example. So let's wait a little bit. It takes a little time. So what is direct kinematics and inverse kinematics? With direct kinematics, we can set the values of each of the angles of the robot. In this case, this is an industrial manipulator robot. It is composed by 6 articulations or 6 joints. And inverse kinematics, it's about direct kinematics. It's about computing the position and orientation of the final tool with respect to the base, and this is done with simple multiplication of transformation matrix. And inverse kinematics is the opposite. We try to find the 6 angles at the same time in order to arrive to a position and orientation. For example, we will change here the orientation of the final tool in, let's say, in that way. And with that orientation, we can move it along the x-axis, the y-axis, and the z-axis. Okay? So what are the mathematical tools behind this basic computation? So first, we need to attach a frame to each link, an orthonormal frame, and then to describe the position and orientation using a transformation matrix. We can use the Navier-Hartenberg convention, which is a standard way of assigning frames, or we can simply attach a frame and move it to the next, and then detect if it's rotating in Y, in Z, in X, etc. And then to add the position vector from each frame to the next. And the magic comes when you simply multiply these guys and you obtain the position orientation of the final frame with respect to the initial frame, or base frame. So those are the basic tools for forward kinematics. For inverse kinematics, it's a little bit more complicated, but it's nice and geometrically attractive method for computing the angles. First of all, we will cope with this 3 degrees of freedom problem. So we have the position of the end frame projected on the floor, and then we can take X, Y, and by noticing that this is the only angle that will be affecting this axis, we can take that Q1, or the first angle, is a tan of minus X over Y. So it is simple computation. Then we will look for this subproblem that is like this. So we have a length here, LA and LB. LB, what is the height of the final tool minus this L1. So we write this, we write down this here. And then LA, it's X squared plus Y squared, the square root. Okay? This is this line. Having this LA and LB, we have this 2 degrees of freedom problem, and then we can compute LC, which is the square root of the square of each side, and then we have the cosinus law from where we can compute this angle. This cosinus law applies to this non-square triangle, to this one. So we have that the square of this one is the square of this one, which is L3, L2, minus 2 times L1 plus times L2 times cosinus of this angle. So from this we can compute this angle, and from this angle we can find this angle, which is Q3. Okay? So in that way we have Q3, and we can compute Q2. Or the second angle is this one. So we can compute beta and alpha. Alpha, we can compute it from this triangle. We have that this opposite side, because we have this angle, this side is L3 times sinus of Q3, and this side is L3 cosinus of Q3, plus this one. So we have this triangle, then we can compute alpha. Then beta is, we can compute it from here, LB, LA, the inverse tangent, or a tan. And then subtracting these two, we will have this difference, which is Q2, the second angle. So this allows us to compute the first 3 angles. But the problem doesn't end there for a 6 degree of freedom. This is kinematic decoupling, and it's based on Professor Spong's book. You can notice that we have 1, 2, and 3 degrees of freedom, and then this 4th will not affect the position of this point, because this will rotate in this. So we will fix there as our end point for a 3 degrees of freedom problem. And then the problem becomes to compute the last 3 joints or angles for compensate for the orientations, and the first 3 to put this point at a desired position. So as an input we have the desired position and orientation of this frame. From there we can compute where this must be. This means that the end effector it will be this one plus this one, and then we can obtain the position of the wrist, which is this one. The problem is that this distance, we can obtain it from the robot, from the characteristic of the robot, but we can obtain it as constant, but referred in the last frame. So we can transform it to base frame with this rotation matrix, and then we can obtain in which position we want the wrist to be. So with that, we can solve for 3 degrees of freedom problem that we will see before, and then to solve for the orientation. That means that with these 3 given, we can compute which must be these 3 in order to arrive to the desired rotation or orientation of the final 2. This is like this. The final orientation is given by the first 3 and then by the last 3. This will be given by the 3 degrees of freedom problem, and this 3 we can obtain it from the following calculations. So we can obtain R from 3 to 7 in this way, and then we know from robot configuration that is a rotation about x, c, and x again. So we obtain this kind of expression. So at the left we will have numerical values. That means that we can make an equation of this true matrix, and then by observing that this cosinus is exactly here, we can obtain theta 5. And then by dividing these two, we can obtain theta 6, like here, R13 over R12, which is this one. About this one will be the tangent of theta 6. So we can obtain those angles. The same here with R21 and R31. So we can obtain this. So this is how this program works. We can compute the inverse kinematics of a 6 degrees of freedom robot. We have some virtual reality here, which show the frames and allows to present in a clear way this kind of computations. And by programming in MATLAB, we can verify our solution. There are many caveats in this solution. For example, this elbow will mean that we need this distance and we need this angle, but we can carefully analyze it, but the main ideas are those that we presented. So why this is important? Because this will be the base for our working algorithm. The key in here, when you can say that you succeed in here, is when you can move one of these without affecting the other. It means that you are computing in an exact way the inverse kinematics. You are moving only on x, but the other positions and orientations stay still. Same with y, etc. So once that you are capable of making this simple calculation, or not that simple, but this computation, we can extrapolate this to a humanoid. In which way? We can say that this is our base frame, and this, the pelvis, will be our end tool. In the similar way, this one can be the base for this other manipulator, or this can be the base for this and this. The main idea is for walking that you have a base frame, which be, for example, this foot. So we have an inverse kinematics to the pelvis. And then, knowing the position and orientation of the pelvis, you can impose the position and orientation of the free foot, and the other way around. You can take this as base, and this is your final tool, and then from here you have another manipulation, 6 degrees of freedom, to the moving feet. So we have 4 inverse kinematic problem, and we can see. For me, this is really nice to show. for example, with Humanoid, which is one of the first robots that I started to work in here in Mexico, which is a nice robot. Another important thing that we can say about this is that the same configuration is, for example, for HRP2, for Honda humanoid robot, for several robots, it's the same combination of angles. So we can see here that if you set the robot in double support, then you are able to move, for example, the pelvis in vertical direction, toward backwards, forwards, and in lateral way, with the same orientation of the pelvis. And besides, you can set the orientation of the pelvis. Check that this point doesn't move, so we are affecting only the orientation. So first rotation, and then second one, and then the third one. So this is the basis for our walking algorithm. And this is based on the resolution of these 6 degrees of freedom and 6 degrees of freedom for the other legs. We can see also the result maybe in here. Okay. And for instance, if I put it in left support, I am allowed to move the right ankle on the right foot. In this way, I can lift up the other foot and set it forward or backward. Okay? Well, so this is how we will manage to generate our own walking for some humanoid. In this case, this is humanoid. This is like CR7 pose, you know. My students did that, like Cristiano Ronaldo pose, like this. Okay. So the same as we did it with the manipulator, we did it with the humanoid, setting the angles and then in joint space and then in the task space. So we have different problems regarding this. So we can assign frames and obtain the homogeneous the transformation matrix. We can see here that the main purpose here for inverse kinematics is to notice all this distance, to get familiarized, to get familiar with all this distance and to denotate different distance for the robot. Then we make the same kind of calculation for humanoid, for biological humanoid. It's the same type of ideas of kinematic decoupling. And we already presented the interface. We can mention that inverse kinematic was presented in a conference paper in 2013, and then this interface, we have the copyrights, like stuff like that, in 2014, something like this. So now that we are able to move the pelvis to where we want and the trunk in the orientation, the same with the left foot. The next step is how to produce walking motions. So we will be using these cycloidal type of functions. This has the characteristic that the velocity and acceleration are 0 at the beginning and at the end. So this will minimize the impacts of when you will be walking. So these simple formulas using sinus, etc., which are these forms, we will be using like a puzzle in order to form the different trajectories. So these are 5 different cycloidal forms in order to produce a walking motion. So we will assume that we will begin with foot or with feet side by side, and then we will begin with a small step, for example, first right, and then we will have the left left foot behind. Pie izquierdo atrás, left foot behind. And then we must make a left step like this. And then we end up with right foot behind. And then we can go another one, or we can simply finish, etc. So this is the possible motion. We will have 1, 2, 3, 4, 5, 6 different kind of footsteps or zancada. First, this one or this one, and then we can repeat a lot of steps, and then to finish. Okay? So the idea here is to produce this kind of movement of the foot with different parameters. We will be able to say how long the step will be and how high will be the step, and the same for lateral motion, etc. For the pelvis, we know that we must put the pelvis in this side in order to be able to lift off this foot. If not, there will be a falling. If I lift this foot by having my weight here, we will be falling this. So first I have to make this, and then this, etc. So this is where the cycloidal forms came into the play, because we have to move here, then stay a little bit, and then go to the other side, etc. And for the height of the foot, we can lift it in the right moment. So these are parameterized trajectories. I am going to be able to tell how long the step will be taken and at which instant we'll be lifting the foot, etc. So this is for stability and rapidity and velocity issues. So we have several position and orientation of pelvis, stand foot and free foot, but some of them are constant, and we have reduced state. This is not the state, but reduced coordinates. So this is what we are going to move. The X, the advance of the pelvis, the Y, the lateral motion of the pelvis, etc. So by composing with these cycloidal forms, we can make these kind of complicated trajectories, but remember that there are 6 different motions. So it's different if I will start with left or hand, or if I'm making a left or right footstep, etc. So this is the kind of functions that we will be producing for our humanoid to walk. So, which is the result of this? We can illustrate it here. And because we are near to the final. So in here, we can check our walking, inverse kinematics, base humanoid walking. So we can walk forward, we can maybe walk like lateral, etc. So this is just playing with the trajectories of pelvis and each foot. This interface can be connected to Bioloid and to check the validity of our trajectories. So, some words on dynamics. What we are proposing is only to based on inverse kinematics to obtain the angles of each joint of the legs, and then to pass it directly to the robot and check experimentally if it is stable or not. This is ad hoc for small human robot that you can manipulate with your own hand and make several tries in reality. But it is desirable for bigger humanoids to compute the dynamics. This means that maybe the Lagrangian model with external forces, and then to check for zero moment point stability, or even with cyclic stability. So this is, for this robot, we believe that this is not necessary, because besides, in reality, this is not will be always exact. So for this kind of robot, we can use only this. But for larger robots, it's recommended to make this. This is motivated, the parametrization, because of in RoboCup, we are dealing with different fields. So you can spend like weeks by adjusting your walking engine, and then you arrive in place and then change the surface, and all your work doesn't work because the robot will fall. And then this is a practical way to rapidly adjust to a new surface, to a new condition. So this is why we propose this simple approach. But for now, for more large humanoids, it is important to predict before experiments if the robot will fall down. And that will not depend only on Q, but on the derivatives, the velocity, acceleration of the angles, and to check some criteria, some stability criteria. For the case now, it's similar, but it has this caveat that it has this joint in this way, and that's no problem for inverse kinematics, but the problem is that there is only one motor for this, so this angle must be the same as this angle. So we are still trying to solve, we can solve it up to here, but in here we are left with 5 degrees of freedom, not 6. So this is a still working problem, but as long as this angle remains small, we can produce stable walking with now that we will be showing in this demo. I hope this will work fine. And with this we will be ending our presentation. I think most of you know now. For those who doesn't, here is the guy. So it's 25 degrees of freedom, and let's check connection.
Hola mundo. Buenas tardes.
How with this interface we can manipulate each of the robot, of each of the motors of the robot. But for the legs, I have no problem with manipulating the arms. However, for the leg, it is necessary to use inverse kinematics. So we will be going to this position, and this is inverse kinematic. So I am able, based on inverse kinematic, to move it in vertical way up to a certain point, backwards, up, forwards, and in lateral. So this will be helping us for walking, also with the orientation, as you can see. Psi is not very good result because of that problem with the pelvis. But anyway, so this is an example. I recall that this is parameterized, so we can make it faster and make it look better. And this is the user that will be manipulating these parameters. So I will make a quick test. Walk. First is to check its balance. This is the fastest. This is It's not advancing, but in here, I'm going to ask for 8 centimeter steps. And let's see how it works. Oops!
Ouch.
Okay.
Ouch.
Okay. This is why it's always a video is recommended. Okay, let's try to do it one more time. That's right. 8 centimeters is observation. So that's our own made walking for now humanoid. And this is stable. We can try to make it faster, etc. Okay, so that will end our talk. Thank you very much.
Thank you very much for a very nice presentation. And if you have some questions or comments,